Section 3.2.1, Inverse Functions and Composition of Functions. One-to-one functions. A function is one-to-one if every output corresponds to exactly one input. If a function is one-to-one, then its inverse is said to be a function. We can also, in order to tell whether or not a function is one-to-one, use the horizontal line test. A function is one-to-one if and only if no horizontal line intersects a graph of f more than once. So if you look at this horizontal line I drew in this first graph that we have, you can see that this does not pass the horizontal line test. Therefore, I know when I am going to graph the inverse that it is not going to be a function, because this problem says we want to graph the inverse, describe the relationship between the function and its inverse, and write the equation for the graph. So again, I know that this is not one-to-one, that it doesn't pass the horizontal line test, and thus the inverse is not going to be a function. So remember, to graph the inverse, we would want to switch our domain and our range, or our x and our y's. So the first thing I did was pick these point values, and I made a table for x and for y. So then, of course, if we recall from the inverse, and remember that's your inverse function notation. So for this, we take these y's, they now become my x's. And then these x values would become my y's. And then the next thing I'm going to do is just going to actually plot these points and then sketch the graph. So I just plotted the points from the table, and then now I'm just sketching the graph. And as you can see, we remember from last year we also did the vertical line test, so now you can actually use the vertical line test to confirm what we said earlier about the horizontal line test and show that this doesn't pass the vertical line test and therefore is not a function. Okay, the last part of this says we want to write the equation for the graph, so I'm going to use the fact that we just talked about transformations of functions, and we know this is a quadratic function, so the parent graph is x squared. And for this, I can see my graph has moved to the left 3 and down 4. So we get y is equal to x plus 3 quantity squared minus 4. And that would be the equation for the graph. Now, if I wanted to find the inverse for this, that's what we're going to do next. We actually, if you recall, switch your x and your y values and then solve for y equals after you switch them. So looking at this, remember that means you are really going to be doing your order of operations in reverse, so PEMDAS. So if I look at this first equation that I have, I first switch my x and my y values. So I get x is equal to 3y minus 2. The next step would be to, do the order of operations backwards, so I want to add that 2 to the other side to get it away from the y. And then the last step would be to divide both sides by 3. So now I get y is equal to x plus 2 over 3. This is just linear, so I know it is a function. So because it's a function, I can actually use my function inverse notation. So f inverse of x is equal to, and we can just separate those. So x over 3 plus 2/3. So then for the next one, we're going to be doing the same thing. So again, switch your x and your y. So x equals y cubed minus 5. We're doing the order of operations backwards, which means I don't want to get rid of that exponent until after I get rid of that 5. So I want to add that to the other side. So we get x plus 5 is equal to y to the 3rd. There was no multiplication or division, so now that's why we're at the exponent. So we get rid of the exponent. We want to take the cube root of both sides. So this would be the cube root of x plus 5. And the cube root of y cubed would just be y. And again, now I can go ahead and use my inverse function notation to get my inverse equation. So in this next one, we're going to do the same thing. Switch our x and our y's first. So x equals y squared plus 4y. This one's a little bit harder because we have a quadratic term, a linear term, and this x over here. So for this one, I actually can't divide a y out because that's not going to help me, and I can't factor a y out because that doesn't help either. So in this case, you would actually want to set it equal to 0 by subtracting the x to the other side. And you would actually want to use the quadratic formula in order to get y by itself. So if you recall, the quadratic formula is negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So in this case, my a value is what's in front of my quadratic term, which is just 1. My b value in this case is equal to 4, and my c would be this whole last term, negative x. Because again, remember, we're trying to write the inverse equation. So now when I plug that into my quadratic formula, I get y is equal to, not x, because again, we have y here, and that's what we're trying to solve for. So y is equal to negative 4 plus or minus the square root of b squared, which is 4 squared, minus 4 times a, which is 1, times c, which is negative x, all over 2 times a, which is 1. And then we're going to just go ahead and simplify this. So we have y is equal to negative 4 plus or minus the square root of 16, and the negative times the negative becomes positive, so plus 4x all over 2. And then notice here the 16 and the 4 have a common term, which is 4, so I'm going to factor that out. So I get y equals negative 4 plus or minus the square root of 4 times 4 plus x all over 2. And the reason I did that is because I know the square root of 4 is 2, so that's going to help me take it outside the radical so I can simplify further. So y is equal to negative 4 plus or minus 2 times the square root of 4 plus x all over 2. And now I can go ahead and separate my terms to simplify further. So y is equal to negative 4 over 2 plus or minus 2 root 4 plus x, or you could write x plus 4, it doesn't really matter what order you write that in, divided by 2, and now I can simplify. So I have y is equal to negative 2 plus or minus, these 2's would cancel out, so root, and I'm going to write this with x first, so x plus 4. And this is not a function because we know that for every input we have the plus or minus there, so we would have 2 output values for that. And I'm going to go ahead and move this so it's not in our way for the next problem. So then for the next problem, we're of course going to do the same thing. So the first thing we want to do is switch our x and our y values. So we get x is equal to 2y over y plus 2. Now for this one, because it's in my denominator, I want to get rid of that by multiplying both sides by y plus 2. And when I do that, because this is really over 1, then I can go ahead and cross these off. So now I've gotten rid of it to the other side, and I can distribute. So I get xy or yx plus 2x is equal to 2y. Then because I have y's on both sides, I'm going to want to leave the 2x on one side and get the y's together because I noticed they're both linear, so it means I wouldn't be able to factor it out. So I'm going to have 2x is equal to 2y minus x times y. And here, again, because these are both linear, I can factor those out to get it by itself. So 2x is equal to y times 2 minus x. And then the last step is to get y by itself. So this is all being multiplied by y. So to get it by itself, you want to divide it onto the other side. And now notice y is by itself because that would cancel out. So we get y is equal to 2x over 2 minus x. And that would be my inverse equation. So as you can see, these do get a little bit harder as we are now in pre-calc. So for the next part, it says when you're solving an inverse equation and you need to take both sides of the equation to an even power, you need to restrict the domain by looking at the original function's range. So restricting the domain, we're going to talk about that. So for a function that is not one-to-one, it is possible to produce an inverse function by considering only part of the function that is one-to-one, and this is what we call restricting the domain. So let's work with something that we're familiar with, which is y equals x squared. So we know that if I were to graph this, we know what it looks like, and we know that this is not one-to-one because it doesn't pass the horizontal line test, therefore the inverse would not be a function. So we're going to purposely pick our own values to restrict it to make it one-to-one, and then find the inverse over that interval. So if it's a quadratic, the easiest thing to do would be to actually figure out where that vertex is, and we know since their parent graph, our vertex is at 0, 0. So I could restrict my graph just to this part that I highlighted and take off this other part in blue, and then it would pass the horizontal line test. So that's one way I could restrict it, or I could restrict it to the right side and take off this part that I highlighted in yellow on the other side. So either of those would work. So let's go ahead and first actually figure out what the inverse equation is. So switch our x and our y. So x is equal to y squared. So get rid of that power, I have to take plus or minus the square root. And now I have my inverse equation. So when I have the negative part of my equation, that would be this side of my graph. So this would be the y equals negative root x. And this side of my graph is actually the y equals the positive root of x. So if I'm writing this out, I would say restrict f of x domain, and we're going to do negative infinity to 0 bracket, then our inverse, so f inverse of x would be equal to what we just said over here, the negative square root of x. So that's one possible answer. The other possible answer would be to restrict f of x's domain to bracket 0 to infinity, because that was the green side that I highlighted. Then f inverse of x would be equal to the positive square root of x, and you don't really need that positive there, so you could just write the square root of x. So those are two possible answers that I could write for this question. Then if I look at number 2, we're going to do the same thing, except we're going to use a different function. Well, same function, quadratic, but we just did a transformation moving it down 3. And actually, let's change that so that instead it would be x minus 3 quantity squared, because then we're actually going to change that interval that we had, because that would move our graph to the right 3. So this is my function, and I've now moved this to 3, 0. So then if I wanted to restrict those values, I could restrict it to this side, or I could do this side. But notice now that the value that I'm restricting it at, the vertex area, is right here at 3, 0. So I could say the first thing I want to do is figure out the inverse. So we get, of course, this was y equals, so first switch those values. So x equals y minus 3 squared. And then order of operations backwards. So in this case, we have to get rid of that exponent before we can do what's in here. So we have plus or minus the square root of x is equal to y minus 3. And then the next step would be to add that 3 to the other side. So y is equal to 3 plus or minus the square root of x. So that means, remember, we have two equations. We have y equals 3 plus the square root of x, and y is equal to 3 minus the square root of x. So for on the left side, we're going to use this equation, and on the right side of our domain restriction, we're going to use this first equation. So we could say restrict f of x domain to negative infinity to, and now we've moved it to the right 3, so 3. Then f inverse of x would be equal to the negative square root, so 3 minus the square root of x. So that's one possible answer. Or we could say restrict f of x domain 2 bracket 3 to infinity, then f inverse of x would be equal to the positive square root, so 3 plus the square root of x. All right, so the last part we're going to look at is compositions of functions. Another way to combine functions is to use the output of one function as the input of another. Of course, we remember doing this last year because that's called composites of functions. So we can write this a couple different ways. We have f, and then notice that's an open circle of g of x. So that could say f followed by g of x, or we could read it as f of g of x. And again, this is an open circle, not closed. We're not multiplying the functions. We're doing composites of functions. So be careful. And then for this one over here, well, first let's go back to this one. Notice that g of x is in the inside. So that means we would actually be plugging g of x into f. And over here, notice that it's g follows f of x, or g of f of x. And in this one, f of x is inside, so that means we would be plugging f of x into the function for g of x. So let's just try with numbers first to remember what we did last year. So we have g of f of negative 2, or g followed by f of negative 2. So the first thing you want to do is evaluate the inside function, which is f of negative 2. So I would plug that into my function into f for x. So we have 3 times negative 2, and always use parentheses when you plug values in for your function. So we get 3 times negative 2, which is negative 6, minus 2, which is equal to negative 8. So then we're going to take that answer, and this is what f of negative 2 is equal to. So we actually plug that in for g. So we get g of negative 8, which is equal to negative 8 squared, and negative 8 squared is 64. So our entire composition answer would be 64. So if we go to this next one, we have f of g of 4, or f followed by 4. And of course, we could also rewrite this as f parenthesis g parenthesis 4. So first, we want to evaluate the inside function, which is g of 4. So g of 4 is equal to, so I'm going to plug that 4 in for x. So I get 4 squared, which is 16. Then I'm going to take that answer, and I'm going to plug this answer into the function for f. So f of 16 is equal to 3 times 16 minus 2. And 3 times 16 minus 2 gives me 46. So then that means that the entire composition answer would be 46. So now we can also do that for the entire function. So for this next part, we're actually plugging the function into the other function. So notice it's f of g of x. We don't have a number here, so we can also rewrite that as f of g of x with all parentheses. So the inside function is g of x, and we were given that g of x is equal to x squared. So really we're going to take that out and replace it with x squared. And just like what you did up here, instead of plugging in numbers, we're actually plugging in function. That's called composite function. So we're plugging one function into another, we're compiling them together. So that means we would have 3 times, and we're plugging in x squared for x into the f of x function, minus 2. So all I have to do here is distribute. So 3x squared minus 2 would be my new function. So we can do the same thing over here, except for notice that we have g of f of x. So that means that the inside function in this case is f of x. So we're going to take that out. And if it helps you to actually write the equation with parentheses first, that's fine. What goes in the parentheses? We know f of x goes inside the parentheses. So f of x is actually equal to 3x minus 2. So I'm plugging that in here. So now that I have that, I can go ahead and simplify. So if I have something being squared here, That means I would have 3x minus 2 times 3x minus 2, and I'd have to FOIL that out. So that gives me 9x squared minus 6x minus 6x. We'd have the inside terms, and the last terms, negative 2 times negative 2 is plus 4. So 9x squared minus 12x plus 4. And there we have our composite function. So the next part, we also, because we're in pre-calc, want to be able to make sure we can find the domain. So we talked a lot about finding the domain of functions. So if I have g of f of x, when you're finding the domain of these functions, you always want to find the domain of what you substitute into the equation, in this case, f of x, and then look to see if it's in the domain of the composite function. So you're going to look to see where they overlap. And for this one right here, notice that g of x is what you're substituting in, so you have to find the domain of g of x, and then look to see if it's in the domain of the composite function that you have. So let's go ahead and do this one together. So we have f of x equals root x minus 2, and g of x is equal to x squared minus 1. So I can use my other notation, so this would be f parenthesis g of x. So I'm substituting in g of x right here. So I'm going to look at that domain first. So the domain of g of x, again, which is what I substituted in, this is a polynomial function, so the domain is actually all real numbers. So we would actually be highlighting this entire line if I was to do that. So again, that's for g of x, the domain. And then, so the next part, I want to actually figure out what this is equal to. So I'm taking out g of x, because I know g of x is equal to x squared minus 1, so I'm doing f of x squared minus 1. And that means I plug all that into x for the equation. So root x squared minus 1 minus 2. So then that simplifies into the square root of x squared minus 3. And that doesn't simplify any further, so this is actually my composition answer. So now I want to look at this answer and see where the two are going to overlap. So recall, when we look at the domain of this, we set it equal to 0 and solve. So x squared is equal to 3. So x would be equal to plus or minus the square root of 3. So on my number line, I would have negative root 3 and positive root 3. Because we can be equal to 0 in our numerator, we know these are closed circles. And then we learned how to find the test values on each part of our number line to figure out where the values are going to be positive. So if I pick 0 because it's in between these two, 0 squared minus 3 I know is not going to work because it's going to give me a negative 3 underneath the radical, which is negative, so it wouldn't be part of our number solution, so I'm not going to highlight here. If I pick to plug in something below negative root 3, like negative 10, negative 10 squared is positive 100 minus 3, which is going to give me positive values. So I know that I can highlight this part of my line. And same thing on the opposite side. If you were to go ahead and plug in 10, it would work as well. So then for this, again, you're looking for where the two are going to overlap. So where do the two overlap? You can see that since this is all real numbers, the place where they're going to overlap would be from here and here. So the domain of our composite function is actually going to be negative infinity to negative root 3, including root 3. So that's why we have the bracket there. So, and then positive root 3 to infinity. So that would be the domain of my composition. So now we're going to look at it a little bit differently. Now we're going to look at it with g of f of x, which is going to give us a different answer. So we have g of f of x if we use the other way to write it. So now we're plugging f into the g function. So we have g parentheses. So what is f of x equal to? If you go back up here, you can see f of x is equal to x root x minus 2. So I'm plugging that into this g function for x. So we have parentheses squared minus 1. So this goes inside the parentheses, root x minus 2. Notice I'm squaring a root, so that goes away, and I get x minus 2 minus 1. So then this becomes x minus 3. So that is my composition answer. So I have to, again, when I'm looking at this, I look at what the domain of what I substituted in. So that, again, that was my g of x right here. So the domain of, or sorry, that was my f of x. We did that in the first one. So f of x right here. So my domain of f of x, so let's write f of x domain. So if I look at that, we can draw our number line. If I solve, I have x minus 2 equals 0, so I'm looking at values of 2 on my number line, which we learned before. I can be equal to 2 because I can have 0 in my numerator. And if I pick test values in this function, I know that something below 2, such as 0, 0 minus 2 would give me negatives underneath the radical, so I know I'm not going to highlight that part of my line. I would actually be highlighting my line starting at 2 going this way. Then if I look at the domain of my composition answer, that right here is a linear function, and the domain of that would be all real numbers, so this whole line is actually highlighted for that second one. So where did the two overlap? Well, notice that they overlap starting at 2 to infinity. So my domain of the entire composition would be bracket 2 to infinity. And again, you have to be careful because we originally plugged in a square root function, and even though we got rid of it by doing our algebra and doing the compositions, it's still a domain restriction that we have. So that's why we still have to be careful about the values we plugged in because of the original square root in the function. So for this next part, you can do this on your own. So you're going to find the composition and then their domain. And then this last part, let's go ahead. Now we're doing this a little bit backwards. It says, write H as a composition of two functions in two different ways. So if I want to do this, I'm trying to figure out what two functions can make up H of x, and then I have to write the rule for it. So I could say maybe g of x is equal to, let's say it's x to the third power. So if I have x cubed, then f of x could be the square root of x minus 5. So to get h of x, if I were to plug this x cubed in for x here, notice I would get h of x. So we would say h of x would be f of g of x is equal to h of x. So this would be one way I could write my composition. Of course, there are other ways that you can write this. So let's try another one. So for another way to write this function, I could say let g of x be equal to, let's do x cubed minus 5. Then f of x would have to be equal to the square root of just x. So now if I plug this into here, notice I would get my composition function h of x. So then I would have to write that I'm doing, in this problem, f of g of x is equal to h of x. And that would be two different ways to write this function. And then you guys could practice this one on your own. And that's it. So we'll go ahead and take a look at this more in class.